Okay, section 13.1, parabolas and circles. So all of chapter 13 is it's all about what we call conic sections. And conic sections are named for cross sections of the cone, so the three-dimensional cone. When you take a slice out of a cone, you can get a couple different shapes. The first couple we're going to talk about parabolas and circles. So we have three things to talk about here. One is graphing parabolas and circles. Parabolas and circles. Number two is finding the radius. Excuse me. And the center. Of a circle. And lastly, we're going to be looking at writing equations in standard form. And this is of parabolas and of circles. Circles in standard form. Now, standard form for conics, for parabolas, is not the same standard form that we're used to for parabola, and we spent a whole chapter talking about parabolas or quadratics. So let's take a look at the two types of standard form for conics, so that you can think of this as the standard conic form. Now the classical one is y equals a times x minus h quantity squared plus k. And this is the one we're used to. The center is at h comma k. Center, it's not a center for a parabola, it's a vertex. Vertex is at h comma k. And we have, if a is greater than 0 or greater than 1, then we have a narrower parabola. Narrower than x squared. Remember, we're always judging it off of x squared. And if a is between 0 and 1, I guess we went with absolute value of a, between 0 and 1, and absolute value of a greater than 1. We have a wider parabola than x squared, so that's just rehashing some of our transformations. So we're not going to spend any time graphing these. We spent a whole chapter, like I said, studying parabolas, looking at equations, graphing them a couple different ways. This is using transformations. The conics use transformations. So in this section, in this chapter, when it's referring to parabolas, it's going to be referring to this form of the parabola. And again, as we talked about in our quadratics chapter, it just makes it easy. You know right what the vertex is. You know right how big your vertical stretch or vertical shrink is based on A. You know what direction it opens. If A is negative, then it opens down. If A is positive, it opens up. The parabola that we're going to be focusing on the most is the other parabola, x equals a times y minus k squared plus h. So it looks very similar, and the nice thing is you don't have to learn what new variables are. They're all the same thing, but this is a horizontal parabola. And this is not a function. So one thing to get out of the way now in this section is all of our conics, except for this standard parabola, are not functions. None of them will pass the vertical line test, starting with the horizontal parabola. Now with the horizontal parabola, as I said a second ago, we don't need to learn new definitions for the variables. The vertex is still h comma k. We just have to recognize that the h is on the outside, opposite of this, and the k is on the inside, opposite of the other one. And if a is greater than 0, then the parabola opens to the right now. And if a is less than 0, the parabola opens left. So if it's negative, it opens towards the negative. If it's positive, it opens towards the positives. So this is the parabola. We're going to graph a couple of these now, and we're going to focus on, just because it's a weird one, and it's not what we studied in the last chapter. Now, there are a couple things to consider that are unique to this. So we have these definitions for the wideness or the narrowness of our standard parabola y equals x squared based on a. This changes if a, the absolute value of a, is greater than 1. It's still narrower. It's still a skinnier parabola. But it's not narrower than x squared. It's narrower than y squared. And if a, the absolute value of a, is between 0 and 1, it's still a wider parabola, but it's wider than y squared. And of course, x equaling y squared, just a quick little sketch, is the parabola that opens like this. It has all the same points as the standard parabola x squared. It's just, think of it as being turned onto the other axis. So let's start with graphing x equals 2y squared. So as we said, the letters, the variables, the h and k's, still the same. So our vertex, there's no h and k's in this, no pluses, no minuses inside or outside. So the vertex is going to be 0, 0. Our a equals 2, which tells us that we are opening to the right because it's positive. And since it's 2, it's going to be narrower than x equals y squared. So let's start this graph by first graphing x equals y squared. And we could talk about a nice way to graph that conic. So we need to give ourselves some axes. Now, because we're opening to the right, I don't need a lot of negative x's. So we're just scaling our axes to fit our needs like we've done before. There 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. 1, 2, 3. So that's -2. That's 2. This is 2, 4, 6, 8. And the way that I like to graph this is cheating a little bit, and I physically turn my paper. So now it's as if I'm graphing y equals x squared. So if I was to graph y equals x squared, and this was the y and this was the x, we go through 0, 0. We go through 1, 1, -1, 1. Now I know that this is actually -1. It's actually 1, -1, but same idea, doesn't change. -2, 4. 2, 4. And then 3, 9. -3, 9. And we have our parabola. Just make my point bigger afterwards. And then turn it back. And we have x equals y squared. Nice, easy graph there. So if we want to graph our conic, x equals 2y squared, this is going to be narrower. And so it does the exact same thing that it always did. Our points get stretched out. Now, it's not stretching the y anymore because it's not y equals, it's x equals, so it's stretching the x values. So if this was the standard graph, we would say 1, 1 goes to 1, 2. Well, our graph is not the standard graph. It's the horizontal version. So instead of 1, 1, it's 2, 1. So this point gets pulled along the x out to 2. So that should be there. This point gets pulled out to 2 as well. So this should be here. This point gets pulled out by a factor of 2 all the way to 8. So this should be at 8, 2 now. Like right there. And this one gets pulled all the way out to 8 as well. So this should be here as well. Our 0, 0 remains the same. And then we just connect the dots. And this is 8, comma, negative 2. This is 8, comma 2. This is 2, comma 1. And this is 2, comma negative 1. And this is 0, comma 0. And the blue graph is x equals 2y squared. So you can almost get away with graphing these by turning your paper sideways, physically turning it sideways like we did to graph the initial one, and graphing the corresponding regular y equals whatever it would be, swapping out the x and the y, and you could get a fairly accurate result. So that's the basic one, 2y squared. Our next graph that we're going to do is going to be x equals negative 3 times y minus 1 squared plus 2. So now we have all the transformations happening at once. So our vertex, first and foremost, this is going to be at h, which is on the outside, comma k. So that's 2, comma 1. And our a value is negative 3. So it opens to the left. And it's going to be narrower than x equals negative y squared. Now I say negative y squared because y squared is this black graph here and it opens this way. Negative y squared is the same thing opening the opposite direction. So when we go to graph, we're going to do this without graphing y squared first. Now since I'm opening left, opposite of this one, I don't need all these positive values anymore. I just need some negatives. Excuse me. I'll give myself a nice negative graph. One, two, three, four. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will be 2, 4, negative 2, negative 4, negative 2, negative 4, negative 6, negative 8. So we can start by plotting our vertex. at 2 comma 1. So I actually do need some positive x's. I need 1, 2, and 2 comma 1 is right here. That's our vertex. So the rules that we discussed back in our quadratics chapter about over 1, up 1, it's the same rules, but now it's not over 1 and over 1, it's right 1, down, right 1, up. So over and up, over and down versus over versus left, up, left, and right up. So negative y squared should come over 1 and up 1, and then over 1 and down 1. But we're stretching that out by a factor of 3 because absolute value of a is 3. So instead of 1, 2, it should be over 1, up 1 times 3, 1, 2, 3. Now an easier way to do this is you could just plot some points if you really wanted to. So we know 2, 1 is the new vertex. So if we plug in 1, we could get some points. The big thing here is what's going to give us the 0. So I'm going to try plugging in negative 1. Negative 1 is 1, 2, 3 away. So that's going back to the multiplying by 3. So my first point, which is normally 1 away, over and down, I imagine it should be here, which is now 3 away. So plug in negative 1, negative 1 minus 1, negative 2. And then, actually, let's stop for a second here and think about this a better way. So we're plugging in, or we want to know points. Let's say if we wanted the x-axis, we'd be picking x values. But since our function, not a function, our conic is x equals, we're actually plugging in y values. So if I wanted to figure out when x was negative 1, if I feel like this should be here, I actually need to plug in 0 for y. So if we plug in 0 for y, we do it down here to the right, we have 0 minus 1 squared times a negative 3 plus 2. So negative 3, this is negative 3 times negative 1 squared plus 2. And that's negative 3 times 1 plus 2. Now this is going to equal negative 1. So my intuition was correct. We do, when y is 0, x is going to be negative 1. So we would go through right here. Now, because we're squaring here, plugging in 0 is not the only way that we get a positive 1. We could also square positive 1. So you can use this to your advantage. What y value, when you subtract 1 from it, gives you 1? Well, that's 2. And we know, since quadratics are supposed to be symmetric across a axis of symmetry, at y equals 2, we also are going to have x equals negative 1. Straight above it. And then we can do this again. So if this was the standard parabola, we'd be over 2, up 1, 2, 3, 4. This is being multiplied by 3. So it should be times 3 should be way over here. But again, my y value is negative 1 here. So if we plug in y equals negative 1, we have negative 3 times negative 1 minus 1 squared plus 2. And that's going to be negative 1 minus 1 is negative 2. So negative 2 squared is just 2 squared, or 4. So this is negative 12 plus 2, which is negative 10. And that's not the only place that would give us the same value as negative 2 squared. We could also do 2 squared. So what minus 1 gives you 2? That's 3. So if we want y to be negative 1, we need to be at negative 10, way out here. I don't even have enough. It'd be up here. And if we want y to be 3, we also need negative 10 for x. way out here. So you can see this is an extremely narrow quadratic. And it would go through negative 10 comma 3, negative 10 comma negative 1. This is negative 1 comma 0. This is negative 1 comma 2. And that's 2, 1. And we have our graph. So the hardest part, and you saw I did it as well, it's really easy to do, is we're so used to plugging in x's for our points. We have to remember when we have this type of parabola, the horizontal one, we're plugging in y's. We're plugging in the y values, not the x values. You got to make sure that you're keeping track of it, that you're plugging in your y's and not x's. I mean, if you pick the wrong number, you'll still get a point and you can still plot it. But we have to remember that we are plugging in y's. So those are horizontal parabolas. Our next conic in this section is circles. So circles are conic sections where every point is equidistant from its center the distance in question is called the radius. And our standard form, so for a circle, with center at 0, 0, the origin, the equation is x squared plus y squared equals r squared, where r is the radius. Again, this is for the specifically circles centered at 0, 0. The nice thing is, when you're graphing circles, we have a trick. Since every circle centered at 0, 0 essentially looks the same, we can graph them relatively quickly. So we're going to graph x squared plus y squared equals 64. And we're going to graph x squared plus y squared equals, let's do 16. So we need some axes, and I'm going to do 2 sets. One for each circle. So both of our circles are centered at 0, 0. The first one, 64, is 8 squared, so it has a radius of 8. So I need to go out to 8, negative 8, negative 8, and up to 8. And the way that circles work, when they're centered at 0, you will always have these 4 points The other points are harder to make, and you're going to see how terrible my circle drawing skills are in a second here. But we just draw a circle connecting these 4 points. It's always this part that messes me up. And then this is 8, 0. This is 0, 8. This is negative 8, 0. I'm sorry, not negative 8, 0. This is 0, negative 8. This one is negative 8, 0. And we have our circle. Well, over here, 16 is 4 squared. So I need to go out to 4, down to negative 4, over to negative 4, and up to 4. And we plot these points, and we make a circle. As best you can. You can see mine's not very good ever. Can't draw circles. And this is 4, 0. This is 0, negative 4. This is negative 4, 0. And this is 0, 4. Now, we don't actually put a point for the center because the center is actually not technically on the circle. But look at what I've done. If you look at these two circles side by side, I have made the circle with radius 4 look larger than the circle of radius 8. Now, because circles all look the same when they're centered at the origin at 0, 0, if you only have these 4 points, you can really change how these look on different axes. Now, if I was to graph this circle on this set of axes, there would be at least 2 more tick points, 4, negative 4, negative 4, and 4. And that circle over there would look like this here on these axes. And now we can get an idea for the scale. So one problem with circles, what this example is trying to nail down, centered at the origin, is that they all look the same. And depending on how you scale your axes, you can make smaller circles, radius 4, look bigger than the larger circles, radius 8. You can't get a true size comparison on 2 different axes unless they're scaled exactly the same. But you don't need to because you can just graph them on the same because they're always going to never intersect. So keep this in mind when you're looking at graphs to always make sure that you're looking at your scale and make sure when you are graphing that your scale is proper. And if you are comparing circles, I would recommend that you graph them on your same axes. Because otherwise you can look at these and go, oh, this one's bigger. But it's not, because my radius is much smaller. I was just more generous with my scaling. So this is an important thing to keep in mind for circles centered at the origin. But that's not the only type of circle that we focus on. In fact, it's probably the one that we focus on the least as a conic, because we can have circles anywhere. So standard form for a circle, standard form, is x minus h quantity squared plus y minus k quantity squared equals r squared. This still has radius r, but its center is no longer the origin. Its center is h comma k. So back when we first did parabolas and transformations, I told you h comma k is the convention that we use for the change in vertex. And that convention comes from conic notation. And it's because every conic that we're going to study in chapter 13, standard form starts with its center at h comma k or its vertex for the parabola at h comma k. The nice thing is you could still graph circles very easily, just like we did these two, by identifying your center and then moving out your radius 4 points in either direction. So let's take a look at an example of that to see what I mean. And I'm going to cheat. Looks like there's some axes on the back of this page. I'm going to use them. So we are going to graph x minus 2 quantity squared plus y minus k, y plus 3 quantity squared equals 9. And if we give ourselves some axes, we can start to identify our important piece of information. So right off the bat, our radius is 3. 3 squared is 9. And our center is at 2, negative 3. So if you remember our old convention from quadratics, when it's positive inside the parentheses like this, it means that the vertex was at the negative number. Same thing applies here. Standard form is a minus sign in both. So when it's plus inside, that means that it actually is negative in your center. So this is plus 3, which makes it negative 3 on the center. So I need some scale. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So this is 2, 4, 6. Negative 2, negative 4, negative 6. 2, 4. Both of these are negative. 4, 6. So we're going to start by plotting our center. 2, negative 3. 2, negative 3. Right there. So now we take our radius, and just like we did on the last example, where we went up, down, left, and right by our radius, that's what we're going to do here. So we're going to go up 3, which brings us to this point here. We're going to go down 3, which brings us to this point right here. We're going to go over 3 to this point here, and we're going to go over 3 to the other side to this point right here. This is 5, negative 3. This is 2, negative 6. This is negative 1, negative 3. And this is 2, 0. Well, now we just make our circle around those points. And again, I hope that you can do circles better than me, because I can never do them well. And again, not going to label the center because it's not technically on the circle. The circle is the ring. And now I've graphed a circle. So it's very easy to graph circles when you are just identifying the center and then the radius. You plot your center, go up, down, left, and right, your radius value, and you can graph your circle fairly quickly. Now, we're not going to spend too much more time here graphing circles. You're going to get plenty of practice in your homework. The big thing with circles is that we're not often given standard form. So when it's like this, you can see it's really easy to graph. Identify your center, identify your radius, plot the center, move out your radius up, down, left, and right, and you can graph your circle. But we want to be able to identify equations of circles. So if we're not given the equation, we're just given the information. So write the equation. Of a circle with a r equals 6, and centered at 1, 1. B, r equals 9, centered at -3, 2. And C, r equals 1/7, centered at -4/5, comma, -2/9. The nice thing is, standard form of circle, it really gives us a quick way to do this as long as we know the radius and the center. Or if we know the radius and at least one point on the circle, we can figure out where the center is. But if we're given the radius and the center, it's always x minus h squared plus y minus k squared equals r squared. So for part A, this is going to be x minus 1 squared plus y minus 1 squared. And our radius is 6, so this needs to equal 36. And that would be the equation of our circle. So for parts B and C, I recommend that you try these on your own. So pause the video and see if you can come up with the equation of the circle. And then check your answer with what I'm about to write down. So part B, radius is 9. Center is -3, 2. So this is going to be x plus 3, quantity squared, plus y minus 2, quantity squared, equals 81. That's our radius squared. Part C, we're centered at -4/5, comma, -2/9. So this is going to be x plus 4/5, quantity squared, plus y plus 2/9, quantity squared, equals 1/7 squared is 1/49. So those are equations of the circles that we were given. Now, the other thing that can happen is we can be given, so like in these examples, we're given the equation, told to graph, given the information or the graph, because I could show you a graph with this and it have its center and its points, and you could figure this out. So given the radius and the center, either in information like this or as a graph, and write the equation. The last step of circles is figuring out whether a given equation is a circle or not. And this is arguably the hardest thing to do with conics because we do them with all of them. So let's say, given x squared plus y squared plus 4x equals 16 plus 8y, determine if this is a circle. Well, we only have one way to do that, and that's to complete the square. So the first thing we're going to do is rewrite x squared plus 4x. I'm going to put that in parentheses, and then plus y squared, and I'm going to move the 8y over by subtracting it, minus 8y, equals 16. So don't get fooled. Just because this is a perfect square does not mean that this is a circle yet. We have to now complete the square twice. So we complete the square twice. So first on x squared plus 4x, and then on y squared minus 8y. So let's start with x squared plus 4x. Remember, we take this value, divide it by 2, then we square that number, that equals 4. And this would be x squared plus 4x plus 4. And then we would have to add 4 here. So we'll come back to that. Let's take a look at y squared minus 8y. So again, we're looking at the -8. First we divide by 2, then we square that, we get 16. So our perfect square would be y squared minus 8y plus 16. So to turn our equation that we had into this, we have x squared plus 4x plus 4 plus y squared minus 8y plus 16 equals 16. Now we added 4 here, so we're going to add 4 here. We added 16 here, so we're going to add 16 here. And we get x plus 2 quantity squared plus y minus 4 quantity squared equals 36. So this is a circle. It's plus x minus h squared, y minus k squared equals r squared. R is 36, and our center is at -2, 4. Now, one thing that's really important when you're dealing with these types of problems where you need to complete the square is the only way that this fails to be a circle is if you end up with negatives here. So negative x minus h squared plus y minus k quantity squared equals r squared, or x minus h squared minus y minus k squared equals r squared, or if they're both negative, x minus h squared minus y minus k squared equals r squared. None of these are circles. Because of the minus. However, x minus h squared plus y minus k squared equals, let's say, big capital R. This is still a circle as long as r is greater than 0. So if this number is negative, it won't be a circle because circles don't have negative radius. But if this r is anything, now we like having perfect squares, but they don't have to be. So if this capital R is something like 10, it's still a circle. Its radius is square root of 10. So keep that in mind as you're working through these problems in the homework. As long as the coefficients on these two terms are positive, and this number is positive, you have a circle. If you have any of these three combinations of negatives on the left side, it's not a circle. If this number is not positive, it's not a circle. But that's it. Those are the only times we don't have circles. It's when we have negatives over here or a negative over here. Technically, when r is 0, it's still a circle. It just has 0 radius. But then that's just a point. Okay. So that is the end of 13.1.